Hi, I introduce a numerical method for financial problem. It's ATI method, that is alternative direction implicit method, and its application on option pricing. So first I introduce the method. So ATI method actually an iterative method, and it has two steps of iteration process that alternately update the column and row space of an approximate solution. And the method is unconditionally stable and there is no unnecessary storage. And that's the figure of the method, actually how it's work on. So it's actually two-step method. So in the first half step, it work on time level I to I plus half. So in the first time level in I, it's actually explicit in y direction, and in the next time level, that is I plus half, it's implicit in x direction. So it's actually store data on time level I plus half on column, and in the next half, that means the second half, it goes to time level I plus half to I plus 1. And in I plus half, it's actually work on x direction explicitly, and the next time I plus 1, it's work on y direction implicitly. So actually it is the alternative method. So in the first step, it works on implicit and explicitly, and the second level, it's alternate the direction and work on explicitly and implicitly in x direction and y direction. To get more clear concept, I use an example of second order PD. So in stage one, it's go to time level n to n plus half, and in x direction, it's time level n plus half, that is the implicit level, and in y direction, so in y direction, the time level n, so it's the treated as explicit. And in stage two, it's alternate the direction in explicit level and implicit level. So it's go to n plus half to n plus 1. And in x direction, it's n plus half, that is explicit. And in y direction, it's time level n plus 1. So it's implicit. And in stage 1, the populate data matrix at time n plus half, one column at a time. And in stage 2, this stage populates the data matrix at time level n plus half in row at a time. And this scheme, the accuracy of scheme in second order in time and space. And if we follow the von Neumann stability test, it's unconditionally stable. And to reduce the computational time, stage 1 form a tridiagonal matrix, similarly stage 2. So here is the tridiagonal form of stage 1 and stage 2. So then I use that method. Actually, that's the fundamental algorithm of the method. So I use that method on a financial analysis. So I choose a published paper that's added in the reference. So here, the author first introduced the Brownian motion, and here XT be the underlying asset price, and sigma be the volatility, and BT is a standard Brownian motion under the Riggs neural measure. And then it's actually the Asian call option price model. So the arithmetic average price is AT over T. Then the stochastic differential equation for evolution of AT, actually AT denote the underlying asset price running sum. So it's DAT equals XT GT, because AT equals 0 to T, integration of 0 to T XTT. Then the Black-Scholes equation for this model, actually it's a pricing model for Asian call option, and Asian call option is an option type where the payoff depend on the average price of the underlying asset over a certain period of time, as opposed to a standard option like American option or European option, where the payoff depend on the price of the underlying asset at a specific point in time. That is the maturity. So in Asian option, allow the buyer to purchase or sell the underlying asset at the average price instead of the spot price. So in the model, there is two condition, terminal condition and the left-hand boundary condition. For the terminal condition of the Asian call option price V equals max A over T minus E. Here T is the expiry date and E is the strike price. And the left boundary for X equals 0 equals the exponential of negative interest rate with T minus T multiply with the terminal condition, that's been the max AT over A over T minus E 0. And then here author only consider the model when the underlying asset running sum between 0 to ET, that's the Black-Scholes equation over the domain, and he split those boundary condition on the separate domain, that is the terminal boundary on the domain 0 to X to 0 to ET, and the left boundary condition, that is when X equals 0, it's on the domain 0 to ET to 0 to T. And the next, that equation actually comes from when A is greater than or equals ET. And the last equation actually for when A equals ET, then that part becomes 0 and we get that part here. And what's X? X be the upper bound of asset price. It's actually typically 3 or 4 times the strike price. So the author considered X as 4 times strike price. And that's the actually model to apply to find the solution of the model. using ADI method, we need to discretize the model, and the discretization in two direction, one in time and other one in space. So first time discretization, and time discretization actually it's a very natural to consider dimension splitting at this time step. So one alternate solves independent one dimension problem in x direction and y direction. So author discretize the above PD in 0 to t using a uniform mesh. I didn't mention mesh here, but the mesh Tn equals n del t. So n is the bounded 0 to k, and del t equals t, capital T over k. So there is two operator, one Lx and La. So from the governing equation, from here, actually Lx denote that part, sorry. Lx denote half sigma square x square, the second order, and the Rx minus Rx, the first order, and the last part. And the La is defined by x del over del A. So to reduce the space, we only use La and Lx. So according to the ADI method, it's work on in two stages. So in first stage, the time split from n to n plus half. Here is the first time level, first stage, time n plus half to n, and that the left part actually a tridiagonal matrix, and that's the boundary condition. And the next stage, that's been in stage 2, the time level n plus half goes to n plus 1, and that's also the tridiagonal matrix form, and the other two equation actually the boundary equation. So from here we get that two stages to time level n to n plus half and n plus half to n plus 1. Actually it demands more discussion here, but I skipped all those discussion. If you follow the paper, you'll get the more clear details about that semi-discretization in time. And the next stage is discretization in space. The same way used here. That's been in stage 1 and stage 2 according ADI formula. In stage 1, it is split time n to n plus half time level, and that's usually a tridiagonal matrix form, and that's the boundary condition. And that's in stage 2, that goes to n plus half to n plus 1. And those are the boundary condition. And here the Lx of the option price in time level n plus half, it's actually split in finite difference formula, finite forward difference formula. And similarly for La operator, we also use the finite difference formula here. And to use two step, that's first one in time and second in space discretization. To use those discretization formula, we find the finally fully discretized formula here, and fully discretized formula for space and time is given here, and I means here in x direction and j means in a direction. So actually I going through from 1 to n and j going through from 0 to m. And so that is one formula. I'm sorry. That's one formula, and that's another formula. So that's formula in x direction, and that's formula in a direction. And using those boundary condition, we find the different option price, and we also calculate the error or ratio. So why you use that formula? What's the benefit of ATI formula? Actually, ATI formula is too much important because of it reduces the time and storage, because when we use the tri-diagonal form, it's reduce the computational cost too. And one more thing, it's unconditionally stable. And another thing is that when we use the ATI formula, actually it's reduced the error so dramatically. Actually, the error goes to point something 1 or 2 digit 0 and then get a value. So its error is very low. That's why we use ATI formula. And then here is the reference that I use, that paper I use in the above. So that's it. Thank you for listening. Have a good day. Bye-bye.